Every day, as we walk down the busy streets of our cities, most of us hardly notice the cast iron circles embedded in the pavement. We may step on them, drive over them, or see them lined across sidewalks, but rarely do we stop to think about their purpose or their extraordinary durability. These are manhole covers. Far more than simple lids, manhole covers are silent guardians of the infrastructure below our cities. They seal the entrances to sewers, storm drains, and utility tunnels, protecting both the networks beneath and the people above. They must resist heavy truckloads, corrosive environments, and decades of wear, all while fitting perfectly flush with the road. But how does a manhole cover go from a pile of scrap iron to a precisely engineered product strong enough to withstand the weight of a 40-ton truck? To find out, we step inside a modern manhole cover manufacturing factory, where tradition meets technology, and where every cover tells a story of both resilience and craftsmanship. The journey begins with raw materials. In sprawling factory yards, mountains of scrap iron, steel offcuts, and recycled metal await their next life. Much of this scrap comes from demolished buildings, discarded machinery, and automotive parts. Recycling plays a key role here, not only reducing costs, but also conserving resources. Before the metal can be used, it undergoes a strict inspection process. Workers armed with magnet detectors and visual checks ensure that non-metallic debris, such as wood or plastic, is removed. Consistency in raw materials is vital, since the wrong composition could compromise the strength of the final cover. Once sorted, the scrap is transported via conveyor belts into large bins, ready to be fed into the melting furnaces. But this is only the beginning. The true transformation will happen in the fiery heart of the factory. The furnace hall is the beating heart of the manhole cover factory. Here, massive induction and cupola furnaces generate temperatures exceeding 1500 degrees Celsius, hot enough to turn solid iron into glowing liquid metal. The process begins when carefully measured batches of scrap are fed into the furnace, layer by layer. As the furnace roars, operators monitor gauges and screens, adjusting oxygen and fuel flow to maintain the perfect melting conditions. To achieve the ideal balance of strength and ductility, alloying elements are added: carbon to control hardness, silicon to improve castability, manganese to increase wear resistance. Each addition is carefully calculated, as even slight variations can affect the performance of the finished manhole cover. Within hours, the once jagged scrap transforms into a shimmering molten mass. When the composition reaches perfection, workers prepare for the next step: pouring. While the furnaces burn, another team prepares the molds that will shape the molten iron into manhole covers. The technique used is called sand casting, a method dating back thousands of years, yet still trusted today for its reliability. The process begins with a pattern, a precise replica of the manhole cover, made of wood, plastic, or metal. Workers pack sand, mixed with clay and resin, tightly around the pattern, creating a negative imprint of the cover's design. The mold is built in two halves: the cope, top half, the drag, bottom half. Together they form a cavity into which molten iron will flow. Before sealing the mold, workers press in fine details: textured surfaces to prevent slipping, city emblems and logos to mark identity, raised lettering for manufacturing codes and load ratings. This is not just function, it's craftsmanship, ensuring each manhole cover carries its own unique signature. When finished, the molds are stacked in neat rows, waiting for the fiery metal that will soon fill them. When the furnace is ready, the moment arrives. Workers wearing heat-resistant suits and face shields maneuver massive ladles filled with glowing molten iron. With precision and caution, the liquid metal is poured into the sand molds. The flow is controlled carefully, as too fast a pour could trap air bubbles, while too slow could cause the iron to solidify prematurely. As the molds fill, the red-hot iron hisses and crackles, releasing bursts of heat into the air. Vent channels within the mold allow gases to escape, preventing imperfections. Once poured, the metal begins to cool, solidifying from the outer edges inward, capturing every line and detail of the pattern. In this moment, the transformation is sealed. Cooling is a slow but crucial stage. Depending on the size of the manhole cover, molds may rest for several hours before they are safe to handle. Rapid cooling could cause cracks or internal stress, so patience is essential. When the time comes, workers break open the molds in a process known as shakeout. Sand crumbles away, revealing rough cast manhole covers still coated with blackened residue. The used sand isn't wasted. It's collected, sifted, and reconditioned with fresh clay and binder, ready to form new molds. This closed-loop process ensures sustainability and efficiency. What emerges from shakeout are raw, powerful shapes, manhole covers born from fire, awaiting refinement. Though the castings now exist, they are far from finished. Each cover is still coated with sand and rough edges from the casting process. First, they pass through shot blasting machines. These enormous chambers fire streams of tiny steel pellets at high velocity, scrubbing away sand, scale, and oxidation. Within minutes, the dull, blackened surfaces reveal clean iron. Next, grinders and cutting tools are used to remove excess material, known as flash, from the edges. Workers ensure the surfaces are smooth and safe, eliminating any sharp projections that could cause injury or affect fit. The covers are now beginning to look like the final product, but more precision is still required. For covers that must fit seamlessly with frames, machining is essential. Computer numerical control, CNC machines trim edges to precise tolerances, ensuring that the cover sits flush in its frame. Grooves are cut to prevent rattling under passing vehicles, while bevels are shaped to make lifting easier for utility workers. The precision here is remarkable. Though each cover may weigh 100 kilograms or more, the tolerance is often within fractions of a millimeter. This accuracy ensures not only performance, but also safety. A poorly fitted cover could shift under traffic, posing serious risks. No manhole cover leaves the factory without rigorous testing. Each batch undergoes a battery of inspections. Load testing. Hydraulic presses apply extreme pressure, simulating the weight of heavy trucks. Covers must not crack or deform. Dimensional checks. Engineers measure thickness, diameter, and weight, ensuring consistency with design standards. Surface inspection. Trained eyes search for defects such as cracks, air pockets, or surface flaws. Sound testing. A simple yet effective method, striking the cover with a hammer. A clear metallic ring indicates solid casting, while a dull sound may reveal hidden defects. Any defective covers are returned to the furnace, melted down, and reborn, ensuring nothing goes to waste. Iron, though strong, is vulnerable to rust. To ensure longevity, most manhole covers receive protective coatings. Traditional covers are dipped in hot bitumen, forming a black, waterproof layer. Modern factories may also apply epoxy coatings or powder coatings, offering enhanced resistance against moisture and chemicals. In coastal or highly corrosive environments, additional treatments such as galvanization or composite inserts may be used. At this stage, city emblems, anti-slip textures, and identification marks stand out clearly against the dark protective finish. The final step is preparation for delivery. Covers are stacked on sturdy wooden pallets, often paired with their matching frames. Each set can weigh several hundred kilograms, requiring forklifts and cranes for handling. Shipping labels indicate the destination, be it a bustling city street, a remote industrial site, or a growing residential neighborhood. Once installed, these covers may remain in service for decades, silently bearing the weight of the modern world above them. If you enjoyed this deep dive into the fascinating world of manhole cover manufacturing, don't forget to hit that subscribe button and turn on the notification bell. We bring you more incredible stories about how the everyday things around us are made, and you won't want to miss what's coming next. Whether it's digging trenches, loading rocks, or breaking through frozen ground, the excavator bucket is the workhorse of any construction site. It takes a beating every day and keeps on digging. But have you ever wondered how these powerful metal giants are made? In today's video, we're heading inside an American manufacturing facility to follow the step-by-step process of building an excavator bucket from the ground up. From raw steel plates to precision welding, from heat treatment to final painting, every bucket is a masterpiece of strength, design, and engineering. This isn't just metalwork, it's a story of brute force, precision craftsmanship, and modern American manufacturing. Let's dive into the incredible world of excavator bucket production. It all starts with raw steel. At the heart of every excavator bucket is high-strength, abrasion-resistant steel, most commonly Hardox or AR400 grade plates. These steel sheets arrive at the factory in massive, heavy stacks, each weighing thousands of pounds. Why Hardox? Because this type of steel can take the pounding. It's engineered to resist impact, abrasion, and wear, making it ideal for earth-moving equipment. Inside the warehouse, forklift trucks transport the plates to the cutting area, where the real work begins. But before cutting anything, engineers load the CAD blueprints of the specific bucket model into a computer-controlled system. Every bucket is tailored for a specific purpose, whether it's a standard digging bucket, a trenching bucket, or a heavy-duty rock bucket. Each design requires different thicknesses, profiles, and reinforcement zones. With the digital layout ready, it's time to start shaping. The next step is cutting the steel plates into precise shapes. This is where CNC plasma cutters come in. Using a high-temperature stream of ionized gas, these machines slice through the steel like a hot knife through butter, up to 2 inches thick. The plasma arc reaches temperatures of over 20,000 degrees. The nozzle moves along the pre-programmed path, cutting out sidewalls, teeth profiles, mounting brackets, and reinforcing ribs with surgical precision. Each cut is clean, smooth, and accurate to within a fraction of a millimeter. Once cut, workers mark each part and move them to the pre-assembly area. Here, operators use grinders to smooth out edges, remove burrs, and prep the surface for welding. But not all parts are flat. To form the bucket shell, the curved scoop that does the actual digging, massive hydraulic presses are used to bend thick steel into its iconic rounded shape. It takes serious force, often over 300 tons of pressure, to mold the steel without cracking it. This is where raw material starts to become a bucket. Once all parts are shaped, it's time for assembly. On the production floor, teams position the shell, side plates, and wear strips using alignment fixtures. Getting the fit just right is crucial. A misaligned edge can weaken the structure or throw off the bucket's balance. Heavy-duty clamps hold everything in place while welding begins. In many modern US facilities, robotic welding arms take over this task. These high-tech machines move with smooth, consistent precision, laying down perfect weld beads across every seam. But human welders are still essential, especially for hard-to-reach corners and final inspection. Every weld must be deep, clean, and consistent. Excavator buckets endure extreme forces, so structural integrity is non-negotiable. Once the main body is together, the bucket's cutting edge is added. This is the hardened steel edge that slices into soil and rock. Often, it's a bolt-on design, so it can be replaced after years of use. Some buckets are also fitted with teeth, interchangeable tips that boost penetration in tough terrain. These are welded or pinned to adapters along the bucket lip. After welding, each bucket is visually inspected, then sent for stress testing. Welding introduces stress into steel. If not treated properly, these internal tensions can lead to cracks or failures. That's why heat treatment is next. Buckets are loaded into large industrial ovens, some as big as a small garage. The temperature is slowly raised to around 1100 degrees Celsius. then held for several hours depending on the bucket size. This heat-soaking process allows the steel to expand, relieving internal stress and aligning the grain structure. Afterward, buckets are cooled gradually in controlled environments. No sudden water dousing here, that would warp the steel. In some facilities, specific areas, like cutting edges, are given additional hardening treatments for increased durability. Once cooled, the buckets are tough, stable, and ready for the next stage, final machining and finishing. After heat treatment, it's time to add the final touches. Buckets are moved to a machining station where pinholes are bored. These holes are crucial. They connect the bucket to the excavator arm. If they're even slightly off, the whole system won't function properly. CNC boring machines ensure that holes are drilled to exact tolerances. Then comes inspection. Technicians check every weld, measure critical dimensions, and ensure that the bucket meets all engineering specs. Some plants use ultrasonic testing to detect hidden cracks inside welds. If the bucket passes all tests, it heads to the paint booth. But first, sandblasting. A high-pressure stream of abrasive material cleans the entire surface, removing any rust, scale, or oil. This helps the paint stick better and prevents future corrosion. Then, industrial-grade primer and paint are applied in thick, even coats. Most factories use powder coating, or two-part polyurethane paint, chosen for its toughness against weather and job site abuse. Finally, decals, serial numbers, and branding are added. Now the bucket is ready to hit the road. Finished buckets are loaded onto flatbed trucks or into shipping containers, ready to be sent to job sites across the country and beyond. Some go to dealerships, others straight to construction firms or rental fleets. From residential builds to highway expansions, from mining sites to demolition zones, these buckets work in the harshest environments America has to offer. And thanks to the rigorous process behind each one, they're built to handle it all. Each scoop, each dig, each lift, made possible by American steel, American labor, and American innovation. Enjoyed this peek behind the scenes? Then hit subscribe and turn on the bell so you never miss a moment from the world of heavy machines, smart factories, and powerful engineering. We break it down. You build the knowledge. Thanks for watching, and we'll see you in the next one. Every part is tested, every function verified. From welding sparks to rolling off the line, it takes over 40 hours to build a single unit. Made in America, built to last, trusted worldwide. Today we take you inside John Deere's advanced manufacturing facility in Waterloo, Iowa, to see exactly how these machines are assembled from start to finish. No fluff. Just steel, skill, and smart technology. This is how it's made. John Deere tractors. Before it became a global leader in agricultural machinery, John Deere was just a blacksmith. In 1837, in the small town of Grand Detour, Illinois, Deere invented something simple, but revolutionary, a polished steel plow that could cut through the thick, sticky soil of the American Midwest. Farmers were struggling with traditional cast iron plows that clogged easily. Deere's innovation didn't just solve a problem, it changed agriculture. As America expanded westward, so did demand. Deere moved operations to Moline, Illinois, harnessing water-powered factories and railway connections. The company grew fast, not just in size but in reputation. By the early 1900s, John Deere had become synonymous with reliability. In 1918, the company built its first tractor, the Waterloo Boy, a name that still